Yo, team. Mr. Messenger coming at you. January 26, 2023. We're going to talk about this most recent lesson, which is like so important. It's called the fundamental theorem of calculus. Okay? And what we talk about, what we add to our knowledge of like derivatives and what it tells us, we've always known about like a sign of a derivative. Tells us if a position is increasing or decreasing. Like a sign of derivative tells us the original thing is increasing or decreasing. Well, now we have an extra layer underneath it, which is the area under a derivative. Tells us how much we go up or how much we go down. Now, why is this how much we go up or go down? Well, we've talked about, and we began this class talking about how much we've moved. And I asked you, like, if Mr. Messner drives in a car this fast, what are the two ways you can find where he moves? Okay? The two ways are taking your velocity and multiplying it by your time. Your other way is to take your ending position and subtract your starting position. Okay? Now, this is easily done if velocity is constant. But if we have a situation where velocity is changing, we at least can understand that v times t, or the area under v times t, would be the representation of the amount that I've traveled. Okay? But unless you have a calculator, you will not be able to find this area. If you have a calculator, you can. You can, in the home screen, either graph. We use 3t squared. We can graph, and we can second calc 7. It's an integral. To the calculator, it means accumulate or find the area. You can tell it where to start and where to end. And boom, it finds an area. This is how far I've traveled. 7 to the right. It says my velocity is positive. My position is increasing from 1 to 2. If this was from 1 to 2, I'm traveling 7 units to the right. Okay, cool. But if you didn't want to do it in the home screen, in the graphing screen, you can do it in the home screen. You go to Math 9, and you get this integral. And again, 1 to 2 of 3t squared. You get 7, okay? Now you notice the symbol they use for area, and finding this area, is an integral. Why is that? Well, because human beings, for forever and ever, when asked to find an area, knew that they had to take an antiderivative to get the position function. And once you get the position function, you can then plug in b and plug in a and subtract them. So it was like an alternate approach to getting this answer. Velocity times time gives you distance. Change in position gives you distance. In this class, we're going to have two options. We're either going to let our calculator get our answer very quickly. This means I move to the right 7. Or we are going to, as humans, if we don't have a calculator, take an antiderivative to get a position function. This is v. This, meaning antiderivative, is what we had to do. We turn v into x. We will then plug in b and plug in a to find the change in position. I use this line, and you will see this line in calculus textbooks saying like, yo, don't forget to plug in 1 and 2 and subtract. When you plug in the values, you will realize that the c is not going to matter. Even though we've always like found c and we are always told like, don't forget c. Well, in reality, if you're subtracting two positions, your starting position, which is c, doesn't matter. you're still finding the change in your position. Sorry, this is 2 cubed, which is 8. This is 1 cubed, which is 1. Boom, 8 minus 1, 7. Okay? And there, you can get this number, and this is why things are complicated in this class. You can get this number, I've gone to the right 7, between 1 and 2, 2 different ways. Using your calculator to find the area is velocity times times, the visualization. But you could also take an antiderivative and find the change in position. Okay? What do you get? You get how far you've traveled. Not really how far you traveled, but how much you've displaced. Okay? I'm going to try to make it as clear as possible with the examples I do so you really are understanding what's going on. And it might take a while, so skip if you're like, I know what's going on, and just go to the answers. If you don't know what's going on, just like pay attention to the details because it'll help. All right. Like, I'm asking you to find the displacement, but I'm telling you you don't have a calculator. Okay? I'm asking you to find how far like you've overall changed your position, but I'm not giving you a calculator. I'm going to just show some visuals to start. So let's just visualize velocity in terms of its graph. 2t plus 1 looks like this. Between 1 and 3. Okay? Velocity is changing. So this v times t is tough to find. But we can see that my velocity, or my derivative of position, is positive from 1 to 3, which means my position must be increasing. Let's figure out how much my position is increasing by finding the area under my velocity, the area under my derivative. Okay, if I had a calculator, I would just type this into it. And my calculator would do a bunch of quick v times t's. You see it like shading it in. Does a quick calculations, adds things all together like that, because it's very powerful. Boom, it'll give you an answer. That is your calculator doing v times t. We as humans can't do v times t because things are not constant. We actually could find this area using geometry, but let's not worry about it. Let's just say, oh, I can't do v times t. What is my option? Well, the other way to find out how far you've traveled, or rather your displacement, is to subtract your ending position from your starting position. So this is why the integral is used for your calculator to find area. We take an antiderivative to find a position function. This is v, this is x prime, this is now x. We will then plug in b and plug in a. I printed out a lot. That's probably my bad. Yeah, I appreciate it. We plug in b, we plug in a. B is our time at 2, which is 4 plus 2 plus c. We plug in a is 1 plus 1 plus c. We realize the c doesn't matter. We have 4 plus 2 minus 2. That's just going to be 4. Now, what does that mean? I increased by 4, or my dude traveled to the right 4. F goes up 4. You can always check your answers while you're doing your homework by breaking out Mr. Calculator, by either graphing or math 9ing. Sorry, it's 1 to 2. That was a bad start, huh? Easy thing about these calculators, you can go back, select, go back to this number 2. Bam, 4. Okay, cool. But now we realize something. And I'm going to, oh no, is that you or me? Cancel it. Sorry, printing issues here. Now we have a great opportunity here. what happens if we have negative 2t plus 1 from 1 to 3? Okay, now I know if I plug in 1 into t, I'd get negative 1. So here's my velocity, and my velocity is negative. Okay, great. Since my velocity is negative, I know my position must be decreasing. If I find this area, I'm going to figure out how much I decrease. Your calculator can find this area. It's not really an area. What your calculator is doing is going to be like multiplying all the v's that are negative by t's. This is really v times t. Oh, this is going to be annoying, but whatever. This is my life. Getting kicked out of my classroom during 6th period. We can't do that. Instead, we can take an antiderivative and plug in b and plug in a. Okay? So we take the antiderivative to get negative t squared plus t plus c. We will not need the c because it'll go away. I'm going to start skipping showing it. Plugging in 3, squaring it, I get negative 9 plus 3. Plugging in 1 and squaring it, and then making a negative, negative 1 plus 1, giving me negative 6 minus 0, so negative 6. Checking this answer, (1 to 3), negative 2 t plus 1, should get negative 6. Okay? Now your calculator gets it very quickly, which is great. But human beings did not have calculators the entire time, but wanted to find areas under derivatives because areas under derivatives tells us how much a function is increasing or decreasing. All right, this is another situation where my velocity is positive. Since my velocity is positive, my position is increasing, I'm moving to the right. The area under my velocity, the area under the derivative will tell how much I'm moving to the right. It will give me my velocity times times. My calculator can do this. We human beings cannot do this if velocity is changing. We human beings can find a change in position because we know the antiderivative of velocity is position. The antiderivative of t squared, 1/3 t cubed, plus c. I won't need the c, it will go away. I'm always going to show it, but I'm going to skip the step of like subtracting it. And I get 8/3 minus 0. So I've moved to the right 8/3. My position has increased 8/3. I ended 8/3 to the right of where I started. Great, let's look at the next one, 3t squared minus 6t. I'm going to just quickly factor out 3t. This is not something you would have to do, but this is good. Okay. 0 and 2, so it'll be below it. Okay, so in this situation, this velocity will go negative and then go positive. Now, this is a very, very important example. It will be negative until 2. It'll be positive from 2 to 3. Now, typically when we do a sign analysis, we like to split things up. We like to say, okay, from 0 to 2, and then from 2 to 3, my velocity goes negative to positive, which means my position goes down, then goes up. The area under my derivative, the area under the derivative, not the area under the position, the area under the derivative will tell you how much the position is decreasing or increasing, okay? But here's what's interesting. I'm asking you for 0 to 3, which means I'm asking you, like, combine how much I moved left and combine how much I moved right to tell me my displacement. Displacement meaning how far away I ended from where I started. Okay, so I'm combining both my left and my right movements to get an answer. Now here's where, calculus and this antiderivative is a beautiful thing. Sure, your calculator will give you the right answer, but taking an antiderivative, giving a position function, kind of incorporates everything that you need. You'll get your ending position minus your starting position. You'll get your change in your position. You'll see overall how far away you are from where you started. So I took the antiderivative to get my position function. Instead of velocity times time, I'm doing position and its change. My x of b, ending position minus my starting position, is 27 minus 27 minus 0. Oh my gosh, is this right? This is great. 0. Getting an answer of 0 is a great answer. Why is getting an answer of 0 a great answer? Because it's telling me however far I move to the right, I move that same amount to the left. Okay? And I ended up where I started. Three seconds later. Let's just confirm it, make sure I did my math right. It might be fun to actually do this in the y equals 3t squared minus 6t. Let's change our window from 0 to 3. Let's zoom fit. Zoom fit is a beautiful thing. Yo, that's great. Second calc, 7, 0, 2, 3. 0. Oh my gosh, it doesn't say 0. It says 2.25 e negative 13. Yo, your calculator's doing a bunch of calculations. It's doing kind of an approximation. Yo, this answer is really 0. Okay, it's like 2.25 times 10 to the negative 13th place. Move the decimal place over a bunch. We've seen in this class before our calculator giving us an answer that's close to, but not exactly on. But watch what I can do. I'm going to regraph this just by deleting x and adding x. It erases the shading. And watch what I'm going to find. Oh, geez, why did I say plus and minus? It should have been minus plus. Let's second calc. Area 7 from 0 to 2. That negative area is negative 4. Yo, my position decreased by 4. Where did I start? I don't know. But I know wherever I started, I went to the left 4. Second calc, let's find the area from 2 to 3. It's going to be the same amount. 4. So, where does this number come from? This 0. Why is this number okay with us? What we are finding, this change in position, being 0, means you went somewhere, you came back to where you started. I went to the left 4, and then I went to the right 4. Cool? Calculator does velocity times time. We can do a change in position by taking an antiderivative. Great. 6 sine t looks like this. 0 to pi. My velocity is positive. If I find the area under the velocity, if I find the area under the derivative, I'll figure out how much I've gone up or how much I've gone to the right from my original function. 0 to pi, 6 sine t. This is a great question. It's like, how much is an area under a hump of sine times 6? I'd get negative 6 cos t is the antiderivative plus c. From 0 to pi, pi is going to go away. Negative 6 cosine pi minus negative 6 cosine 0. I feel like I gave you the same problem. No, this is positive 6. This is minus negative 6. I get 12. You get the same answer using your calculator. The area under the velocity gives you velocity times time. We are finding velocity times time using change in position. Honestly, I could put right here change in position, which tells me how much I moved. Ooh, this is fun. 0 to 1, 6 sine pi t. I'm assuming that this is the same deal. It's just like 1, we we get to the sine of pi, which is 0, so it's like this. So again, velocity positive. Here, this one, I went to the right 12. But this is good practice. This is v times t. This is the area. We are going to find it by taking the change in position. Now, let's remember, you have pi t on the inside. If you're taking the antiderivative, you need to multiply by 1 over pi. Let's find x of b minus x of a, the change in position. That is like the other way to find how far I've traveled. I get negative 6 over pi cosine of pi minus, the c is going to go away when I subtract, negative 6 over pi cosine 0. This is positive 6 over pi plus positive 6 over pi. 6 piths plus 6 piths are 12 piths. So I think that with my velocity being positive, my position is increasing by 12 piths. 6 1 over pi is 6 1 over pi is 12 1 over pi's. Yeah, let's just see. 0 to 1, 6 sine pi t, close your parentheses. Boom, calculator does v times t's, does it quickly. I mean, that's quickly, but like in terms of calculator, it's not like automatic. It doesn't happen like right away. There's a little bit of a pause there. Boom, 12 over pi. All right, that's how far we increased. Now, eventually, human beings discovered computers and discovered ways to program doing thousands of calculations quickly. And maybe instead of doing thousands of calculations, they discovered how to do like complex calculations even simply, so they don't have to do as many. And so all of a sudden, when the calculator and when the computer was invented, human beings had the way to actually find this without taking an antiderivative. So all of a sudden, like worlds opened up. It's like, yo, if I have some complex velocity function and I want to figure out what's going on in terms of like movement, how much things are increasing or decreasing based on this derivative, I can program my calculator to find the area underneath it quickly. And stuff we're going to be doing will be like graphing complex derivatives, these very complex derivatives. I'm not going to be able to take the antiderivative of that. I don't want to anyways, right? Graphing these complex derivatives, zoom fit. Understanding like the signs of the velocity. But then combining that with our knowledge of areas to know how much our original function x, which we don't know because this derivative is so complex, how much it's changing. We can combine this area knowledge with all just as like one point to get an understanding of like where you are and where you've traveled based on this derivative. That's seemingly complex, but instead, let's just do some calculations. Let's go ahead and go from 2 to 8 and find this area and just understand what it means. You're going to move to the left an amount. You're going to move to the right more. You're going to move to the left more than that. You are going to end up, after all that movement, negative 0.885 units to the left of where you started. Okay? Now, there's a key thing missing with this. We don't know where we start. We do know we're negative, then positive, then negative. We do know my position's decreasing, increasing, decreasing. Where do we start? We don't know, but we definitely go to the left a little bit. We go to the right more, but then we go to the left more, so I end up negative 0.885 to the left of where I started. Okay? If you wanted to, and what we will be doing is we will be finding these locations where we change signs. I'm graphing y equals 0 so I can find the 0 quickly. Second calc intersect. We'll be doing this a lot next class. Which I'll be doing another video for. 2.712, like at that moment, I changed directions. Okay? Now if I went from 0 to that number, I'll figure out how much I went to the left. And then I go from this number to this number, whatever it is. I'll figure out how much I go to the right. And then this number to this one, I'll figure out how much I go to the left. Add those three numbers together, boom, you get like the overall displacement, which you can find just like quickly, just adding up all your v times t's over this entire interval. Okay, I hope this is making sense. Like I'm really trying to over-explain things for the benefits of you young children. Because it's important. This is like super new. It's a whole new level to our sign analysis, derivative understanding. Let's look at t sine t, just so we can see it. Four to seven. Zoom fit. Velocity is negative, then positive. Okay, positions decreasing then increasing. I'm decreasing more than I'm increasing. My guess is that this overall displacement, this change in position, is going to be negative, which means I will end up to the left of where I started. Let's second calc 7, 4 to 7. This change in my position, it's not telling me where I'm located. It's telling me how far away from where I started. That's very important. I'm over-explaining again. But this is not where I'm located. This is how far away from where I started. And we'll get to different problems soon. That incorporates, where am I located? Okay? All this is telling me is how much I go up and down. Let's go back into the home screen. You can go ahead and analyze this, but I don't want this video to last 2 hours. I'm sure there are plenty of sign changes with this, because it has sine in it. This is not something you want to take the antiderivative of, so we're not going to. A lot of stuff is going to happen. I have to do this. I have to do this. It just really helps me understand the number and help me explain to you where this number is and where it comes from. Zero, 2, 3, zoom, fit. The velocity is negative, then positive, then negative. I go to the left, my position's decreasing, increasing, decreasing. We can see I go to the left a little bit because these velocity times times is a little bit of area. I go to the right a lot. I go to the left a little bit. I end up 5.845 units to the right of where I started. It's not a position, it's a change in position. Okay? There's a lot of movement going on. There's a lot of changing of directions. This is telling me how far I ended up away from where I started. 0, 2, 3, t squared cos t plus 2. I ended up 1.047885. It's like, I don't even know what x is. I don't know what x of t is. I can't take the antiderivative of this, and even if I wanted, even if I could, I don't want to. But I know what the change in position is. I know it's this area under my velocity, and that's 1.047, and that's telling me how far away I end up from where I start. Okay? And now, after doing that, understanding what we're finding with these areas is how much I'm going up and how much I'm going down. We are going to start to incorporate a position. Like, hey, what if you know where you start? What if you know I start at a position of 4? Now tell me, where do you go? Okay? Everybody, I hope you're paying attention. Like, now's the time to like unpause the video and pay attention. This is like super duper important. Okay? In the past, for the first quiz, you've done this. Like, I asked you what's x of 3, I told you x of 0 is 4, and I gave you v. In the past, you've been able to take the antiderivative of v, and you get negative t squared plus 3t plus c, and that's your x of t formula. I either told you, hey, there's an initial position at 4, or you'll just say there's x of 0 is 4. You plug in 0 for t, you get 4, and you have your position function. What is our position at time 3? 3 squared, make it negative. 3 times 3, boom, 4. That's a lame problem, okay? But it's fun. It's not lame. It's not lame. It's fun, okay? Now, watch another way to do this. My velocity from the 0 second to the 3rd second looks like this. Okay? We have a positive velocity until 3 halves, and then we have a negative velocity from there. That's my derivative. That means my position is increasing then decreasing. The area under my derivative, the area under my velocity will tell me how far I've gone to the right and how far I've gone to the left. Well, now I know where I started. I started at a position 4. Let's break out our dude. My dude is at a position of 4. This is a position. This is not a number line. These are not t's. These are positions. The dude will travel to the right an amount. We can figure that out. The dude will then travel to the left an amount. We can figure that out. And then, since we know where he started, we'll know where he ends if we just incorporate those movements. Now, what does that mean? If we have a calculator, and we know that our calculator can calculate this. This is done with a calculator. If we could use our calculator, okay, this can be calculated. If we know this is equivalent to this is the other way to find our displacement, change in position. Well, if you know a starting point and you want to find an ending point, guess what? Add your starting point to your displacement, how much you've moved relative to where you began. And you have a beautiful formula. An unknown ending that you're trying to find equals a known starting point Now, this is when we start from the previous problems. We talked about how much we've moved relative to where we start. Well, include where you started to how much you moved, which you can find using a calculator. And boom, you can get this answer 4 or any other answer really quickly. So, my unknown position at 3 equals my known position at 0 plus my displacement, or my change in my position, from 0 to 3. X of 0 was 4. Using your calculator, this is telling you how much you've moved. You can't see it, but it's really 0. This is your calculator saying 0, which means I'm ending up where I started. Now, I hate this problem. I hate this problem because I don't want it to be the same answer. So let's just change it. Ready? I'm going to change it. What is x of 5? Okay? I got C was 4, and I hate when like C. Well, C is 4. That makes sense. I hate when the answers end up the same. Let's find x of 5. Now, this is great because if I keep going to 5, I know I'm going to the left more than I go to the right. I can just kind of tell by the areas. Okay? Here we go. X of 5. Negative 25 plus 15 plus 4. That's negative 10 plus 4. Negative 10 plus 4 is negative 6. Okay. We found that position by taking an antiderivative, finding C, and then plugging in 5. Watch me find that same position simply by saying, oh, what is my displacement from 0 to 5? That's negative 10. That means I end up 10 to the left of where I started. 10 to the left of where I started. Add that to my starting position. If you end 10 to the left of where you started, boom, there's your answer, negative 6. Now, if we wanted to go in depth, let's go in depth. I know I'm over-explaining, but I want this to make sense, and I hope it does. Let's just graph. Let's look. Here's the graph of V. Negative 2t plus 3. Yep. Let's go from 0 to 5. Let's zoom fit. Beautiful. I know this is at 1.5. That's when this is going to equal 0. So 1.5. Watch this. Second calc, 7. 0, 2, 1.5. 3 halves. 2.25. Yo, I went to the right 2.25. Okay, well, now I know my position at 3 halves. My position at 3 halves is 4 plus 2.25, right? Because you started at a position of 4. This is telling me how much you moved. Now, I know my position is 4. 6.25. Or 4 plus 4 plus 2.25. Then, from 1.5 to 5, I'm going to get a big negative number. Negative 12.25. Again, this is the area under my derivative. Well, that means I went to the left 12 from this position, giving me my new position at time 5. 6.25 minus 12.25, boom, negative 6.
This is where I'm like,
Okay? If we have a known position and we know how much we've traveled, or not how much we traveled, but where we end versus where we start, boom, we're good. We don't know what our position at 8 is. we don't know a position function because we can't take the antiderivative. And even if you did, like, you wouldn't want to here. Don't try. But I do know my position at time 2. And if I then add my displacement or my change in position, which is the area under my derivative, a known plus an area under derivative, unknown. We looked at this earlier. I'm just going to look at this one, and then we'll just do the other ones really quickly, because these are quick questions to do. I just want to make sure you understand what's going on, because it's important. Times are 2 to 8. Why is it 2 to 8? This is the time that we start and the time that we end. Zoom fit. Okay, my velocity is negative. I move to the left a little bit. I move to the right a lot. I move to the left even more. I think this is when we ended up like 0.88 away, right? Did we already do this 2 to 8? Did I set up this homework perfectly? I did. Yo, this number, this negative 0.885, does not tell me my position at time 8. This told me how far to the left I went versus where I started. Good job, Mr. Messner, setting up this homework. Well, now I know I started at 3, and I ended up 0.885 to the left of where I started. Add those two together, and it's like, okay, you started at a position of 3. You ended up to the left there. Boom, you'll have your new position. It's probably best to do these calculations in the home screen. We already did this. Oh, did I? Yes, I did do this. No, I didn't do this on the home screen. Well, if you did it in the home screen, it's nice to grab it. I don't know how many we did in the home screen. Two to 8. T to the 2/3. Cos. T plus 2. dt. Is that negative 0.885? That's not a new position. That's how far away I am from my starting position. My starting position was at 3. My new position at time 8 is 2.114. Okay. Did we do t sine t? Yes. There's t sine t from 0 to 1. Oh, well, whatever. Now we're doing it from 4 to 7. We could have done this earlier in the homework. From 4 to 7. $3.814. So this 4 to 7. Why is it 4 to 7? That's a time, and that's a time. From 4 to 7, this area under my velocity is positive 3.819. That is not a position. That is how much I've moved relative to where I started. I started at a position of negative 2. If I start at negative 2, add this amount I've moved versus where I started, and you will now have your unknown position at 7. We can do this just by knowing areas, and areas can be found quickly using a calculator, or not very quickly with humans by taking antiderivatives. Okay, did we do 40 e to the negative t? Yep. Do we do 0 to 3? Yep. What did we say up here for 0 to 3? 5.845. Bunch of stuff happened. Move to the right, move to the left, move to the right. But putting it all together, I ended up 5.845 away from where I started. To the right. Well, now I know where I started. I started at 3. I'll be able to find my unknown by having a known start and adding my change, my area under my derivative. Area under my derivative, total change. 3 plus 5.845. $8.845. That's where I ended up. How did I get there? There was stuff that happened. My velocity changed, so I had to go to right a little bit. Go to left a little bit. Go to right more, so that I ended up to the right of where I started. Cool. T squared cos t. Did we do that one? Yep. 0 to 3. Yep. I ended up 1.047 to the right of where I started. Where did I start? At -4. This is a position at a time. This gives me this area under my derivative. This gives me the change in my position, how much I went up and down. Overall, I went up 1.047. Again, this is like v prime, or v, which is x prime, which tells me about x. I don't know if it's positive or negative, but like overall, I know what x did. X went up 1.047 from 0 to 3. But there's some stuff that happens in between, I'm sure. Negative 2.952. All right. What if you know a position in the future? What if you know a position at time 6? Okay, well, let's think about this integral from 0 to 6. Let's think about this area, this displacement. Okay. Let's look at this. Perfect. 0 to 6. Why am I picking 0 to 6? Those are times. Zoom fit. Okay, I went to the left. Then I went to the right. I went to the right more than I would go to the left. Go to the left a little bit more. It's going to be tough to explain, but let's just see. Second calc, area from 0 to 6. I'll end up going to the right, I think, overall. 3.147. Okay, what does that mean? I end, remember, this is the same as an x of b minus an x of a. I end 3.147 to the right of where I start. Okay, well now let's think about this. I'm going to break out the number line, which like confuses people because like I'm talking about positions. And again, this is a position of 3. This is a position. This is not a time. This is a position of 3. Here's my dude. This is my dude at a position of 3 when time is 6. Okay, cool. The dude ended 3.147 to the right to get to this position of 3. I'm asking, where was he at a time of 0? Well, if he had to go 3.147 to the right to get there, he must have started at like negative 1.47 as a position. Doesn't that make sense? Yes. Now watch how the calculations work. My unknown ending equals my known starting plus my displacement. area under my derivative. But now I will know this, not know this, and know this. How do you solve for this? Subtract. Instead of adding the positive 3, we'll subtract. We're going to go in the opposite because we're coming from the past. Here's my position at my start. 3 minus that, 3.147. I wonder if this is saved as a y. No. It's saved as something. 3 minus 3.147. Negative 1.47. Okay? So, understanding, if you know where you end up and you want to know where you came from, you're going to subtract your displacement. You're going to do the opposite. If your displacement is positive, you ended to the right of where you started. Okay? If you know where you end, subtract that distance and you'll get where you started. If you know your displacement's negative, you end up to the left of where you started. Okay, well, if you know where you ended, add that number to get where you started, right? It's just do the opposite. Okay, again, it's all about times. Time of 4 is I know this position. Time of 1 is what I want to know. I can find how much I've moved in between relative to where I started. Okay. This I know is -2. This is where I ended. Let's find this displacement so we can maybe talk about it the other way, with the ending versus starting being to the left. Bummer. Okay, well, this is telling me I ended to the right 1.556. Since I ended to the right of where I started, and I know that I ended at -2, the position of -2, go to the left 1.556, and you know you'll have to come from -3.5. Where does that calculation come from? Right here. You're subtracting versus adding. You're doing the opposite. Cool. Let's look for a negative displacement. Come on, negative displacement. I'm sure I've done this one before. There it is. Okay. 0 to 3. Why is it 0 to 3? This is the time that I know a position for. This is the time that I don't know. These are positions, these are locations on our number line. Another +5. We need a negative number. Okay, so if between my start and my finish, I move to the right 5.845, and I know I ended at the position of 5, well, if I move to the right to get to that ending, then go to the left to know where you start. Subtract. Do the opposite. Here are the calculations that, doesn't have to make sense to you. I'm trying to make them make sense so that you know what your answers mean. And that'll help you with the graph problems too. I ended up at a position 5. I don't know where I came from, but I know that I moved to the right overall this amount to get there, which means I must have come from -0.845. I must have started at -0.845. Then, over the course of my velocity changing sign, over the course of my position increasing or decreasing, over the course of adding numbers and subtracting numbers, I would have overall added 5.845 to my starting position of negative 0.845 to get my ending position of 5. T squared cos t, t squared cos t, t squared cos t. No! Gosh, come on. I want a negative. I don't see it. Again, hopefully you understand, like, if there was a negative displacement, you're going to have to start to the right so that you ended up at that spot. So if your negative displacement ends you at a place to the left, then you add that negative displacement to go back in time to figure out where you started. But that's not the case here. So I ended up at negative 4. I moved to the right to get there. Don't add that number, subtract that number. Show your work though. Oh shit. 2 to 4. 2 to 4. Maybe I did change it. 2 to 4. 2 to 4. Come on. Come on, negatives. Come on, Mr. Messner's homeworks. Yeah, we did it! Oh yeah. It's the little things in life as a math teacher, guys. 2 to 4. This area under my derivative is negative 11.978. What does that number mean? This is how far I ended. I ended to the left 11, ended to the left 11 from where I started. Okay. I started somewhere. I traveled to the left overall. I might have done some stuff in between, but like after moving around, I traveled to the left, 11.8. I ended at a position of negative 4. This is where I ended, at a position of negative 4. This is a position at a time. The time is t equals 4. Well, I must have started at t equals 2 at a position 11.978 to the right of where I started. Add that number to negative 4. Don't subtract it. Oh, it's beautiful. Mr. Messner knows what he's doing. Sometimes I don't think I do. Or subtract that negative number. Add 11.978. Add 11.978. X of 2 gives us 7.978. This makes sense. I started here. I traveled some stuff. I ended up 11.978 to the left of where I started. Bam. Okay. Find the positions of the particles when the particle changes directions. Ooh. Yo, I'm going to say this. I'm only going to do one of these. I'm not going to do like 5 if there's 5 times we change directions. What do I mean by changing directions? How do you change directions? Well, if your position changes from increasing or decreasing, when your velocity or the position's derivative changes sign, you're going to have to change directions. You go from right to left, left to right. Okay. Let's break out our friend. Let's go from 0 to 8. Please tell me there's 1. Mr. Messner, why did I do this to myself? I should be zoom fitting. I did not. And why did I give you x of 5? Oh, because I'm cruel. All right. Yo, here we go. I'm doing it. Just this one because I know some of you are skipping around and you're getting to this problem. My velocity, or my derivative of my position, is negative, then positive, then negative, which means my position is decreasing. I'm going to the left, then increasing, then decreasing. I need to find these locations. Now, how do I find it? They are zeros. There are two ways to find zeros. Second calc 0 is one way. I don't like using that way. I prefer, because we're going to do this a lot, to graph y equals 0. You don't see it, but it's there. Y equals 0 is on the x-axis. Now, because y equals 0 is graphed on the x-axis, I can find the intersection. Second calc intersection. You could find 0, go to the left and go to the right. Some of you are cool with that. Now I go to the intersection. Oh. Enter, enter, enter. And I get this number. Yo, that number is so big and so complicated that I need to save that because I bet you I'm using it in the future. That is stored as x. I'm going to store it as a. Rewind and fast forward if you don't know how I just did that. I am going to find this other intersection. Second calc intersect or this other 0. Pop over here. Enter, enter, enter. And this is at 5.853. I'm going to store that as b. I would recommend you do that as well. That x, store that as b. Fantastic. Now here's a fun thing. Go back to the graph. Let's find our area. Second calc 7. Let's go from 0 to a. Yo, you are figuring out how much you've gone down and up. I've gone down 2.077 to get to this time. So this is how much x has gone down. You can then second calc 7 a, sorry, go back. Second calc 7 a to b. That's how much you are going to the right. You can second calc 7b to, where am I ending? 8. You can figure out how much you're going to the left. Now, like, I don't like how I gave you x of 5. Like, on your homework for next class, I usually gave you something else, like x of 0 is 2. Which I do on the one on the right, so we'll pay more attention to this on the one on the right. For this one, I think I did this on purpose so that you can like find a time in the past and a time in the future. So really what you need to focus on, and I'm going to go back, but this is fun just to do. So if I started at a position of 3, I would have subtracted 2 to get to a position at this point of 1.07, and then I would have added 5 to get to around like 6 or something, then I would have subtracted 5.7. Overall displacement of -2 around there. Anyways, sorry. To do this one though, like, depends on what you want to find. Do you want to find a thing in the future? Well, like, the thing in the future I can find by taking my known position in the past and then finding the change between those two. Hope this is not freaking you out. It's like all this work I probably should have done for nothing, and I probably should do it over here, but I wasn't paying attention, so. 5 to b of t to the 2/3 cos t plus 2. Okay, 1.04. That means between the 5th second and the 5.85 third second, I went over 1.054. I know I started at 3. That means, based on this, I went to 4.041. If you wanted to do the other one, I'm not going to do the calculations for it, but my position at 2.7123. That's a position in the past. So your past plus your displacement there, which is what I would have found here, would give you, 5, would give you your unknown or your known future, and you would have subtracted those two. Don't like this problem. This makes it too complicated giving you this position at 5. I probably should have given you the position at 0. Why don't we just work with it at 0? I'm sorry for changing it, but I like it because I like this work that we did. X of 0 is 3. That means X of 2.7123 when we first change positions is 3, which is my position, plus negative 2.077, 0.93. Then if we want to find my position at 5.853, I would add 5.219 or whatever, 259, whatever that number is, to that number. To say, like, I went to the left, I started at 3, I went to the left 2, I went to the right 5. This is how much my position is decreasing, how much my position is increasing. This is so important. I don't even know if this is right. Whatever. Rewind. This video is already too long anyways. But it has to be. The other ones are going to be easier. 40E. I think the free response problems are quick too, because it's just like one part. You've done most of the parts, or you don't know how to do most of the parts. Window 0 to 4. Please, Mr. Messner, have one sign change. Can we not have 2 sign changes? It's going to be 2, I can tell. I'm so cruel. Yo, if there's 3, I'm out. All right, good. All right. My velocity, the derivative of position, is negative, then positive, then negative. That means my position decreases, increases, decreases, which means I go to the left, right, left. Let's find these intersections. 1.989. That's 1. Store that. Let's store that as B because it's my second number I'm going to use. Second calc intersect. Goes back to the graph. Go up to go to the y equals 0 graph. Enter, enter, enter. Oh. Uh-oh. Uh-oh. Stop. Unlock. All right, there we go. 0.145. Okay. Since we have a position at 0, this is great. If I find my position at 0 and add my displacement from 0 to 0.145, I'll get my position at 0.145. Now, 2 things I could do. I can either continue to go from 0 and find my displacement from 0 to 1.989 of x prime, area under x prime, area under v, or I can take my position at 0.145 and then add my displacement from 0.145 to 1.989. So let's just do the calculations first. Did I store that as A? Nope. X, store that as A. This is important. Let's math 9 it so I can have the numbers. 0 to A of 40. We're doing a lot of this in the next homework. Hopefully I've done a good job of explaining this in this lesson so that we don't have to explain it as much when we do the next lesson, which talks about like when am I furthest right or when am I furthest left. Okay, so I went to the left negative 0.343. I know I started at a position of 3. I add that, and now I have my position at 0.145. This is 2.656. Boom. Okay. Now, let's go from A to B. A to B. 9.009. Okay, if I know my position at A, and I know that my position increases, because I'm finding the area under the derivative, the area under the velocity. If I know my position increases that much, I'll know my position at time B. 11.665. So started at 3, went to the left a little bit, went to the right a lot. Okay? And then I go to the left a little bit at the end. Or a lot at the end, I have to remember. Now here's the other thing I could have done. 0 to B. Overall, how far did I end at the second time we changed positions from where I started? Negative 8.665. Yeah, that's 9 minus this number. Okay, well, if I do my position of 3 plus how far away I've traveled versus where I started, I get that 11.665 a different way. All right. There's a lot of work doing all that stuff. I understand. But hopefully you get it. Hopefully, when you see a velocity graph like this, you're going to be like, thank goodness, this is so easy. Look at my velocity. It's positive until t equals 3. It's negative until 5. It's positive from 5 to 6. That means my position, because this is the derivative, is increasing, then decreasing, then increasing, which means I'm going right, left, right. But now, they gave me the area under my velocity, the area under my derivative. I go to the right 5, I go to the left 3, I go to the right 1. How much my position's increasing or decreasing. What is the displacement from 0 to 6? Well, if you went right 5, left 3, right 1, 5 minus 3, right 5, okay, boom. Left 3, I got to 2, add 1, I go to 3. So those, you add them all together. 3. I ended up 3 to the right. That's not my position, though. I started at a position of 2. Look at that, right there. You see that? So now let's break out my position graph. This is not a time graph. This is a position graph. I started at a position of 2. At time 0. Over 3 seconds, I move to the right 5. I'm now at a position of 7 at t equals 3. I then, here's my dude, move to the left 3. So now, 7,654, I'm at my position at t equals 5. And then I finish up moving to the right 1. At t equals 6, I'm now at a position of 5. So like 2, add 5 goes to 7. Starting at a position of 2, I go to 7, I go back down to 4, and then I go up to 5. So x of 3 was 7, right? I started at a position of 2. I moved to the right 5. This is how much I've increased. It's not where I am. I started at 2, add 5, I get to 7. I then went to the left, and then I went to the right. I ended up at 5. 2 plus 5 is 7, minus 3 is 4, plus 1 is 5. Started at 2, over to 7, back to 4, up to 5. If that didn't make sense, do it yourself, okay? This is just how far I've moved, not where I am. Hopefully you're like, I got this. My velocity is negative, then positive, then negative. 1, 3. My position, because this is the derivative, must be decreasing, then increasing, then decreasing. The area is given to me The area is under the derivative. The area is under the velocity. Tell me I'm going to the left 2. I'm decreasing by 2. I'm increasing by 6. I'm decreasing by 3. Yo, they're telling me where I am at 3. Now, this is fun. From 0 to 4, I displaced 1. So I ended up 1 to the right of where I started. But then they're asking me where am I at 0 and 4. Okay, ready? Here we go. At time 3, I'm at 2. Okay, so here's a position of 2. This is a position graph. This is not a time. This is not a time. This is a position. This is like the dude on my number line. This is a time of 3. Okay. I go to the left 3 from 3 to 4. Okay, that makes sense. From 3 to 4, I went to the left 3. So I'm going to move 3 to get to the position of -1 when time is 4. Okay, but to get to my position of 2, I had to move 6 to the right between the first second and the third second. To get to this position of 2, I had to move 6 to the right, which means I must have come from a position of -4 at t equals 1. To get to this position of -4 at t equals 1, I went to the left 2, which means I went to the left 2 to get there. I must have come from a position of -2 at t equals 0. Let's see. If I start at -2, move to the left 2, I get to -4. Move to the right 6, I get to 2. Right where I'm supposed to be, x of 3 is 2. And then I finish off going to the left 3. All of these can be found, if you wanted to, if that's confusing to you, by saying x of 4 equals x of 3 plus what is my displacement from 3 to 4, the area under x prime, which is v. 3 to 4 is -3. This is 2 plus -3. -1. What's x of 0? Well, I know the displacement from 0 to 4. 0 to 4 was 1. I know I end up at a position of 2. This is in the past. Subtract 1, I get to that position of 0 to 3. Sorry, 0 to 3. What am I doing? 0 to 3, 0 to 3, 0 to 3 is left 2, right 6 is 4. Subtract 4, you get -2. Sorry if you can't see that. You get -2. How do I get that -2? Like, I got it right there. There's my position of -2. If you understand motion, you can understand this. I'm trying to be fancy with this one. Displacement from 0 to 4 was 3. The distance from 0 to 4 is 13. What is 1 to 3? So we haven't really talked about distance, but like, I don't know. If the displacement from 0 to 4 was 3, and I go to the right 6 and the right 2, well, if you go to the right 6 and the right 2, you've gone to the right 8 total. I only want to go to the right 3 total. Added 6. Subtracted some amount. Added 2. How do I get to 3? I must have subtracted 5. Other ways to do the calculations, but I think this just makes more sense. Does that make sense? 6 plus 5 plus 2 is 11 plus, yeah, so like right 6, left 5, right 2, we're good. Okay, now I can do part D. It says no calculator. I'm going to use my calculator. What is the position at time 4? Position of time 4 equals, I know the position at time 0 is -2. Take my position of -2 and add my displacement. This is a good question, though, where it's like you could take the antiderivative and find C. I believe I talked about that This is your setup. I'm not doing a problem. I'm tired. I've really over-explained things. I hope it's so important. I have to over-explain it. Now I can do part D. Find the position of the particle the first time it changes directions. Honestly, I don't have a calculator, so this is easy. First time it changes direction is when velocity equals 0. This is t minus 5, t minus 3. So it first just changes directions at t equals 3. Like, you have a position function. Oh, hold the phone. That's position of p. Literally, this is just like your test question. This is your q position. Beautiful. I should give you a calculator. So I'll do both. The other one I'm not going to do. This one is a good one. This is more like your actual test question. Two ways. Let's do it without a calculator, and let's do it with a calculator. Yo, my velocity of q is t squared minus 8t plus 15. X of 0 is 5 for particle q. You take the antiderivative of velocity, which you can do, is 1/3 t cubed minus 4t squared plus 15t plus c. Yikes. X of 0 is 5, though, so that's easy. You know that c is 5. I know I'm going fast now, so. This is a great example of, hey, what kind of problem is this? It's free response, right? This answer is sufficient. That's my position at time 3. Like, I don't have a calculator. I don't have time to do all these calculations. I want to do 9 minus 36 plus 45 plus 5. I don't want to do it. Free response, you can leave calculator ready answers, calculator ready. But I'm going to use my calculator really quickly and show you what this answer is. I'm going to type it in, but also show you the other way to find this, where it's like, yo, this area from 0 to 3 under this velocity will tell me how much I've displaced or how far away I am from where I started. That's 18, okay? I know I started at 5. I must have ended up at 23. Well, let's see. One third times 3 cubed minus 4 times 3 squared plus 15 times 3 plus 5. Oh my gosh! Oh my god! That number, which is sufficient on free response, is 23. Two different ways, guys. No calculator, antiderivative. If you want to find an area, you have to take an antiderivative if you don't have a calculator. If you have a calculator, boom, 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 boom. They just splice it up really quickly and add things together because they're so cool. Newton was cool too. Do part C, find the position at time 0. Ooh, that's in the past. I have a position at time 4. That's great. Well, I can find my start by first, like, let's just think about 0 to 4 of v being x prime. And let's find that number. And let's think about it, because it's so fun. We're having so much fun thinking about math, honestly. I have struggled teaching this in the past. I would used to just give out formulas, but it's just like never hits hard until you really understand things. If you understand things, you'll take that with you. What are you taking with you? An area under a derivative tells you how much you're going up or going down. So important. Okay, 5.815. This is 5.815. So I ended at a position of 2. This is a position graph. This is not a time graph. This is a position graph. This is where I'm located. I ended at a position of 2 at a time of 4. I moved to the right to get there. Where did I come from? 2 minus 5.815. Or you have this understanding, initial plus displacement, how much you've moved. This is just how much you moved. It's not where you are. You know you're at 2. You don't know where you start. You know you traveled this much. Subtract. Negative 3.815. Run expression involving, I'm not going to worry about this S of t part until unit 8, but let's just find our position. And now we're using S for position. So instead of x of t, it's S of t, like straight line S. They keep going back and forth between S's and different things. They usually use x though. So position at time 5. Okay, and I have a calculator. I know S of 0. And I'll know how much I've moved relative to where I started. That's it. I'm not doing it. You do it. That's it. We did it. All right. How long was that video? It was long. This is using it. I hope this worked. If this didn't work, I'm going to cry. Later, team.